So hello students, my name is Arun Preta. I have done my mechanical engineering from Thapar University, and today I'm going to discuss a very important topic with you. Very important topic of physics, and that is work. Okay, so I hope you can see. Yeah. So what is work? So let us see the definition of work. Okay. So that is the definition of the work. Work is the transfer of energy into a body that causes displacement in the body. Okay. So as you can see, suppose this is a body. Okay. And suppose there is some force F acting into a body. Okay. So the displacement in the body is X, right? So the work would be given as F X cos theta. Okay. Can also be termed as the dot product of F vector and displacement vector, force vector and displacement vector. Okay. So this is what work is. So you can see energy is the capacity to do work, and work is when a force is applied into a body, the transfer of that energy that causes the displacement of that object. So this is what work is. Suppose, let me give you a real life example. Let me give you an example. Suppose this is a soccer player, okay, and suppose he kicks a ball, and this is the ball gets into a displacement X. So he does some work on the ball. Okay, he applies of some force, the ball displaces, and there is some work. Okay. So as we know that work is F X cos theta. So what will be the conditions of zero work? The conditions of zero work will be if theta is 90 degree. Then the work done is zero, because if suppose this is the angle at which the force is applied, okay, suppose the force is applied downwards, okay, if he applies the force from the top like this, there is no displacement and there is no work. Okay, there is no work done. Even if there is some displacement, that is something else, that is maybe some frictional force that is done by the ground. So that is the work done by the ground. That is something different. We wouldn't call it that he has done the work on the ball. Okay, so first condition is this. Second condition is F is equal to 0. Suppose if the ball is coming from here, he didn't apply any force, maybe he just gently touched it, but the ball is going with its own velocity, so that is also zero work is done. And second is X is equal to 0. Suppose if he kicked the ball but somehow he missed and touched it slightly, so no force is applied and no displacement, so the work done then the work done is also 0. Okay, in that situation the work done is 0. So there are a lot of things, and it necessarily doesn't mean that always the force is applied in the direction of the displacement. Sometimes suppose if this boy in the gym is lifting a dumbbell. Okay, so this is a dumbbell. So here he's lifting a dumbbell upwards, but the gravity is acting downwards. Okay, so the work can also be negative. Gravity most of the times is doing negative work. Sometimes it's positive. If I throw this chalk downwards, so the gravity is doing positive work, but if I lift it upwards, it's doing the negative work. Okay. So now we will discuss the problem. Okay. So here, for an inclined plane with an inclination of 37 degrees, okay, we have been given that the mass of this block is 10 kgs, and in two cases. In the first case, the force will be applied parallel to the plane, and the displacement would be 2 meters, right? And in the second case, the force would be applied at an angle to the plane. So we have to see what are the two forces exerted and what is the work done. Not the force exerted, but we have to see how much work is done in the two cases. Okay. So first case is parallel case. Okay. So here I'll draw the free body diagram. I hope you can see. So here, this will be the force acting mg downwards, which is the weight. Okay. And here, mg sine theta. And mg cos theta. Sometimes here a lot of students get like confused, like why here it is mg sine theta and why it is mg cos theta. It should be opposite. Well, I'll explain why. So you can see, suppose here it is an angle theta, right? So suppose I can find a midpoint and I can just draw like this, okay? So this is a right angle, okay? So here it will be 90 minus theta. How it will be 90 minus theta? Because we know sum of triangle is all the angles of a triangle. The sum of all the angles of a triangle is 180 degrees, okay? So if we need to find this angle, we know this angle is 90 and this angle is theta. So it is 180 degree minus 90 plus theta, okay? So value of this angle will be 90 minus theta. Got it? So here is 90 minus theta. Now, if here is 90 minus theta, so the component here will be, obviously the component here will be mg cos theta, but it is mg cos 90 minus theta. So when it is cos 90 minus theta, here it becomes sin theta. We know this much of trigonometry, right? And here it is cos theta. Although it was sin 90 minus theta, but it became, I hope you have learned this much. Or you can just remember it, cos 90 minus theta is equal to sin theta. Okay? So this is the explanation for this. Now the force, we will assume the force to counteract this force. So the force will be mg sin theta, right? And we have been given that the value of sine 37 degrees is 3 upon 5. Okay, 3 upon 5. So the work done will be mg sine theta into the distance, which is 2 meters. Okay, so the mass is 10, the gravitational force is 10, so it is 3 upon 5 into 2. So it is 100, right? So the final answer would be, here the final answer would be 100 upon 6 upon 5, okay, 20, so it's 120 joules. So that is the energy, that is like the energy, or not the energy, sorry, the work done in case of the parallel force. Now, I hope you can see this. Now we will see for the force at an angle. So this is the angle. Suppose I can show you here. Right, this is the force exerted. So suppose this is the force exerted. So this makes an angle theta. Okay, the same angle with the block. So how will we say what is the work done? The work done would be, okay, so the work done here in the direction of the force. So the force in the direction of the displacement, right? In the direction of the displacement would be F cos theta. Okay, so it is F cos theta into the displacement that is 20. But we here can say that F cos theta is equal to, okay, F cos theta is equal to your mg sin theta, right? Mg sin theta. Okay. Here, let's not consider this one. We'll just find the force. Okay. So here, F is equal to mg tan theta. No, it was wrong. I had read first was wrong. So mg tan theta, right? Mg tan theta, because we have to find the force F, the value of the force F. Okay, here we are not considering about the angles. We're just considering about the straight force because we are assuming the angle to be 0. Because we are taking the force in the direction of displacement, so there is no angle. Okay, that approach is much better. So 10 into 10. So what can be the value of, if we know, like, yeah, so if we know 3, this is 3 and this is 5, so what is the value of the base? Suppose we know sin theta, right? 3.5, sorry, 5 is here, 3 is here. Okay, so what will be the value here? We can just 25 and root 25 minus 9, it's going to be 4. Okay, so tan is 3 by 4. 3 by 4. Okay, 5 5 is 25, 25 3 is 75. This is the value. Okay, 75 Newton is the value of the force. Now, the work done, we're going to find the work done. We're going to find the work done. So, the work done would be 75 into 2, that is 150 Newton. So, you can 150 joules, Newton meter or Newton meter. Okay. You can see more work needs to be done if the force is not applied parallelly to the slope, which makes sense because extra work is being done to, you know, to pull it to the slope, to like push it to the slope, because yeah, a lot of energy is wasted because a lot of component is wasted in the vertical direction. Okay, so this makes sense. This was a very basic example. Now we are going to discuss a very important topic, that is variable force. Okay, what is a variable force? Like work done with a variable force. Here we have to use the integral, because we can see, as you can see, yeah, in ds factor, like, because the force is variable. If it's a variable force, suppose this is force, this is displacement, right? So here we need to use the, because the area under this curve is the work done. So we need to use a like integration here, because if it was like this, if it was a constant force, then we can just simply, you know, do F into S. But here we can't do it. We have to use the integrals. Okay. Yeah, there will be cases where we get variable quantities. So here we can see, I'm going to just, you know, suppose there is this kind of an example. Suppose force given to you is like this, A plus Bx. This is the force, and suppose the displacement is like from here to here in the like one direction. Okay, we can just one dimension, so we don't consider angles. X1 into and from x1 to x2. Okay, so then work done has to be like this. Integration is, we are doing definite integration from x1 to x2. Okay, so A plus bx Okay. So this one, did you get it or not? This is a very basic example. Okay, this is a very basic example. We are going to study one more example. Okay, a little bit advanced with a little bit of higher difficulty level. Okay, so here, what is given to us? Mass of an object is 1 kg. Displacement of the object is variable. Variable displacement 1 upon 3t square, or no, 3t cube. 3t cube. Okay. This is the displacement of the object, that is variable displacement. 1 upon 3 into t cube. Mass is 1 kg. Now we have to find the work done in the first second, right? In this time interval. So, what we will do? First, we just know one equation. That is the very basic equation for the variable quantities, right? F into dx. We don't have an equation for the variable distance. We don't have that equation. Okay. So now, forget all this. Let's use some equations that we learn on kinematics, in the calculus approach of kinematics. Let's forget all this. V is equal to dx upon dt. Now we are differentiating this function. So 3t square, right? You know the basic differentiation. 3t square upon 3. So velocity comes to be, or dx by dt comes to be t square. And what is the acceleration? The acceleration is the double differential of x, right? What is it? It is 2t. Differential function. So this, we have these values. Now we consider this equation again. Okay. Okay, suppose there are these definite integrals. We put the limits of x is equal to 0 and x is equal to 1. This is a time interval, like displacement in time interval 0 and time interval 1. Okay, some imagination we have used. We don't know these exact values, just for the sake of understanding, we are doing this. So F is equal to ma, right? Ma into dx. Okay, now what we are going to do is, let's multiply it and divide it by dt. Okay. It is the derivative of t. Okay. So what we can do here, a comes out to be 2t. Okay. And dx upon dt comes out to be t square. Right. Here we have dx upon dt, right? You can see dx upon dt. So here we will again substitute the value. The mass, okay, 2t and t square. So now we have the correct format that we need, because we only have the value of t, not x. Okay, we only have the value of time, and I have created this whole integral, like converted this whole integral into the time variable. Okay, so we don't have anything to do with the x now. Okay, so that's what we had to do in this. Mass is 1 kg, so let me substitute the values. Okay, and here is 3t cube divided by dt. Okay, so here what we get here, 2t cube, I'm sorry, 2t cube. Okay, so here we get t raised to the power 4 divided by 4, here it is 2, putting the limits 1 and 0. So it is 1 by 2 equal to 0.5 joules. So that's the work done in the first second. Okay, so I hope you like this numerical. I hope you have noted it down as well. Now we are going to study one question that was asked in JEE Mains. Okay, a very simple question. Okay, very simple question. Nothing very fancy about this question as well. So, force of an elastic is given by this. This is how the force of an elastic is given. And we know that, okay, what we know, first let us discuss. This elastic is stretched to a length, like the extension of the length is L. Okay, so we need to find the final expression. We need to find the final expression of the work done when this elastic is expanded to a length L. That's all we know. And A and B are constant, X is a variable. Very simple question, very simple question. But what we need to know is that for an elastic, there is a potential energy. There is a potential energy. Okay, and work done. So there is a different approach as well. Change in potential energy is also equal to the work done. Okay, and the equation is given as final potential energy minus initial potential energy is equal to the negative work done. So this is a convention where we use a negative work done, as you know, this is just a convention, nothing more than that. Okay, so this is a convention where we call it as a negative work. Okay, why we call it as a negative work? Because when we extend, right, when we do the positive work, there is the negative, like the energy, the potential energy stored, it is in the negative direction, right? So the energy that the negative work has been done, right? Because we do a kind of the tension, or you can say the elasticity of the band does the negative work. Okay, so that's why we use this convention. But it is, you know, it's not that hard and fast rule. We have different kind of, in chemistry you'll see, and in physics you'll see some different kind of considerations. It just matters like what kind of system we are considering. Suppose we are considering the force, because in physics we usually consider the force, so we take it sometimes as a positive work, but in chemistry we consider the system, so we take it as a negative work. So it's all about the assumptions, okay, our frame of references. Don't worry about that. So here we'll just do what we'll do. We'll integrate and here we have ax plus bx cube upon 3. Okay, so here it is al plus bl cube upon 3. Sorry, here I have done the integral is wrong. Okay, I'm sorry. Yeah, so ax square upon 2, right? Because so here it is al square upon 2. So this is a very simple question, which is from the topic work done by a variable force, right? So let me write the final expression. I hope you. This is the final expression. The work done is AL square by 2 plus BL cube by 3. This is a very simple question which is based on the topic work done by a variable force, right? So we will use many such examples in the future lectures so that we get a good knowledge and good grasp on the concepts. So this is the end of the lecture right now. Thank you very much.